right, welcome everyone to the Very Large Array. To your left is a sculpture that is a rendition of the array's footprint. The array is made in this Y formation. Once we get up to the balcony, you'll see the configuration it's in right now. The antennas can be moved around. So right now they're in their most compact configuration, which means the antennas are fairly close together. They can be spread out over a surface area of several miles. The Very Large Array is an array observatory. That means we don't care so much about the image that comes out of one antenna. What we care about is the image we can get by combining the signal from all of the antennas together. So basically, doing an observatory in this fashion gets us a level of resolution that we just wouldn't be able to do with a single antenna. Your resolution, meaning how small of objects that you can see, is limited by how big your observatory is. So you could have one giant antenna that's like, a mile long, but you're probably not going to be able to afford that amount of aluminum. So instead, you build a bunch of little antennas spread out over a mile, and then you combine the signal for all of them to get you an image of a similar level of resolution to that mile-long antenna. Behind me is our control building. So this is where the signal from all those individual antennas is combined. There's a supercomputer called a correlator that correlates the signal from all those antennas. You'll learn more about that later. The other thing that is very important in this building is the operator station. So there's an operator on site 24/7. We are observing as much as we possibly can. Radio observatories like this one can and do observe during the day. So we are observing right now actually. So we're gathering scientific data right now on the observatory. And you will actually see the antennas moving as sort of they track objects across the sky. We can't see the stars, but they're still overhead, and they're still moving over our head as the Earth rotates. One of the other cool things you'll see about these buildings is you see those rods up there that are held by those cables. Those are lightning rods. So those are to prevent lightning strikes hitting the building and causing some sort of interference or for the building operations to go down. They were installed by NASA when the VLA was acting as a downlink station for the Voyager mission. So during the Voyager mission, they were doing these planetary flybys, right? And these flybys were only going to happen once. So they absolutely want to mitigate any risk that the downlink station would be disrupted in some way, because there had to be constant communication during the flyby missions. So that's why NASA installed those lightning rods. Okay, any questions before we move up to the balcony of what question I get? There were other downlink stations. I believe this one was actually the secondary station during those flybys. So they had at least two. And then the other thing is, as you can imagine, that as the Earth is rotating, sometimes you have good line of sight and sometimes you don't. So they would have to update the station. Sort of a network station. Any other questions?
What are you observing now, and what's the farthest resolution you've got?
Those are both really good questions. Right now, they're probably working on the VLA sky survey. So we're currently working on an all-sky survey, so that's mapping the entire sky with the Very Large Array. And so this is going to be a legacy data set that will be useful for scientists for years to come, hopefully. And within that data set, we'll be looking for anything that has sort of variability, change over time, as well as sort of reference observations for future studies.
So, are you okay with the size?
I think I'm okay with this. It's about the same.
Yeah, I know. So Brian had a crazy one, so I split Brian's halfway. That's why you're
Okay.
okay. Sorry.
What's the farthest resolution?
What's the best resolution? I don't know. Chris Shaw? Oh, okay. You're asking what's the farthest thing to see. That's a really good question. So in astronomy, we will start to measure distances outside of the galaxy. We'll start to measure distances in something called redshift. So as the universe is actually expanding, and so that causes light waves to become longer as these objects are moving further away from us. So we start measuring distances in redshift, basically how much longer that wavelength has become. I don't know exactly what the farthest is, but I believe the VLA has worked on high redshift projects, so that's stuff in the redshift range of like 3 or 4, let's say. So I apologize, I can't give you a good distance on that, but it's hard to relate that to sort of downward distances. Once you get extra galactic, you have to start measuring things differently. Okay, we are going to make our way up to the mountain.
Of our astronomer, and this is, of course, the control building where we take all the signals from each antenna, digitize, sent down a fiber, put into a electronics rack that splits it up and sends it into a steel vault filled with our LiDAR correlator.
So this is a picture of our correlator, because our correlator is inside a sealed box because it generates a lot of radio frequency interference, and we are a radio observation. So the two kind of disagree with each other. Inside this giant steel box, about 2,000 square feet, is about 40,000 processors. The computing equivalent of about 10 million laptops goes here. Wow. Or if you know the lingo, it's about 20 peta operations per second, which is a 10 with 16 zeros after. That's how many operations it does per second. It was purchased for about $20 million from the NRC, which is the National Research Council of Canada. They built our correlator for us. It's very nice of them. It consumes about as much power as about 150 US homes. And is still technically not actually a top 100 supercomputer because it doesn't do floating point. It only does integer operations. So it's a little asterisk, but it would still be, if it classified, it would still be in the top 100 of supercomputers, which is pretty good for something that we bought 15 years ago and it's kept out in the middle of nowhere. It takes in about 5 gigabytes per second, give or take, from each of the 27 antennas, so about a DVD per second from the antenna goes into this. And then coming out of this is 1 terabyte worth of data per day that we have to keep forever. We have everything we've ever observed since 1976, which currently is about between 4.5 and 5 petabytes. When we go to NGVLA, that number will be exceeded within a month.
Wow.
NGVLA will make more data in a month than we've made in 50 years.
Wow.
Yeah, that's frightening. It's a challenging number, is what it is.
Yep. So we have to go there, we have to make the equivalent, the next generation correlator, has to deal with a bit more data. You want more bandwidth. So it has to deal with a bit more data per antenna, but 100 or 10 times more antennas. And then the processing after that gets a lot more complicated. So we will need to have a whole new super class data center somewhere to deal with the output.
How many people would have to work to get all that out? Like,
It's roughly, we have a certain amount of staffing,
Yeah.
so Rachel, who went away for a bit, is one of our data analysts. We have a team of data analysts that help set up observations, so the scientists from around the world and even public citizen scientists can propose to use our array, help set up the observation, set up the files that control where the antennas look at what time. Those are run by the operations here, the operator. Then it goes in real time. This thing is just a through processor, and signals go through it, and eventually goes to another computer array. Yeah, goes to another array, cluster computing, that sums it up over time into the terabyte per day, that can then be sent down to our data center in Socorro. There, the analyst team monitors the running of the pipeline, which calibrates the data, turns it into the equivalent of pictures of the sky, but in radio waves, and that's then available for users and put in our long-term archive. So,
As far as the number of people, I don't know what we'll need for NGVLA, but right now there's NRA or VLA total, there's about 50 people that work here at the site. Down in Socorro at the office there's about 150. Hopefully we won't need 10 times the people for 10 times the vision.
Are you gonna have Socorro maybe to train more people to help with that system? Because that would be
So there's almost certainly, I mean, there's been a relationship between the VLA and New Mexico Tech, which is the college down in Socorro. It's a science and engineering college. I graduated from there. Lots of people graduated from there that work at NRA. I imagine that relationship will continue.
I'm
All right, let's make our way downstairs. Thank you.
And as we move these pins further and further out, so 22 miles, this is what that's what we see is only the very small stuff. But the software, we take all 4 data sets, put them together, and make an image that shows most everything. It takes about a year and a half to get all this data because we change configurations about every 4 months. So let's see, this antenna over here. This is aimed down where you can see the so the radio signal comes down from the sky, hits the big dish, and is reflected to that reflector up at the funny shape, some reflector. And that's shaped and can be moved. So it chooses which of the frequencies you want to observe. So it rotates between which one. And the signal then goes into one of those horns. Those big things you see sticking out from the dish. It goes down in the horn to the bottom of the horn where it hits the first amplifier. That amplifier is cooled at almost 0 degrees Kelvin. 4 degrees is unbelievable what we do now. The sign over there says 12 degrees, but it also has words that suggest signs. So, it's that first very close amplifier. It gets amplified several times. There's a string of amplifiers, and that gets digitized. Put on fiber optic now, and goes over to the computer to get the control. It used to go on something we call a waveguide. That waveguide was really expensive. 1 foot, $100. $1979.
Yeah.
And we have 21 miles. 21 miles. 19 miles of that stuff. It was one of the big expenses. The railroad track. Something like 20,000 miles. much.
Yeah.
It's a railroad.
Is a group of different receivers. Each one is specific to a different band of frequency. So anybody that wants to come in and make noise, right in the center, it is amplified. Just to, get a little experience.
You need to move out, Lars,
Oh, okay, well, like
And you should talk there.
Yes, that's
Can you hear me now?
Yes.
So, this is, as I said, a prototype, a piece of history, one of the precursors to the antenna as you see them now. And the antennas as you see them now are just the precursor to the NG-VLA, which is in the design phases. If you saw the prototype antenna that's over there, that is going to be one of 263 antennas spread across 5 states into Canada and Mexico. Those are going to be stationary. They're not going to be on track like these. So that's going to cover a whole lot more area. So, any questions?
When was this made?
This
Or the original,
the original?
or the prototype? Is what-
Okay.
The original prototype.
So, in the mid to late 70s was the design and construction of the first antennas.
Okay.
So, there are actually components in the current antennas that are from that era.
Okay.
So what I do, I'm not so much on the sciencey side. I'm in the manufacturing, and I repair and build prototype circuit boards. So I have had circuit boards from the antennas that have been in service since the early 80s come in for repair and rework. So everything from then until the prototypes for the NGVLA, as the designs are finalized, they will come in and I will assist in building what will be the future of
Yeah.
what we do here. Yes, sir.
How do you deal with obsolescence?
Very carefully. A big hammer. A big hammer.
Big hammer.
Okay, so what happens there is if we can find somebody with a stockpile, we will buy what we can. If not, we will try and work with the design and find out if there's a way to separate that and wire around it to maintain the functionality of the rest of the board. It's called blue wiring. So if we have a component that is no longer viable, I will run a wire from here to here around it in order to maintain the rest of the board's usefulness until the rest of the board is no longer functional.
Do you have your own stockpile of like discards that you can search through?
Sort of. But a lot of the time, when one piece goes on an older board, it domino effects.
Yes, because they're the same age.
And the ability to test each individual component is not something I currently have. But eBay is not a good place to buy components. But yeah, so if we have something like that, it's like the next thing to do is have some involves new designs, new components, and me building the prototype and going, hey, it works! So, okay. Anybody else?
So there will be the new one will be in 5 states, but right now are the 5 states.
Currently, the VLA is what you see here.
So it's not in the other states.
They have not been put down. There are no rules yet. Okay, somebody over here had a question.
Is that really in shape?
Yes. That is the current design.
So the collector's at the bottom.
Okay. It is an incomplete demo model.
Thank you.
So the Minecraft shape is actually what they were going for.
It's worth mentioning that these are non-set antennas, which means the light is gathered towards the center, while the new design, the new antenna, is an offset antenna, so the light is intentionally being focused at an angle.
So, any other questions?
How often do you do routine maintenance?
Actually, they have maintenance days once a week, occasionally twice a week. So, if you have the opportunity to go over to the antenna barn, which is at the other end of the tour line, you can see where they bring one of the antenna into the area where it gets serviced essentially top to bottom before it rotates back into service. So it's one at a time, but they have maintenance once a week or twice a week, depending on the schedule that they maintain here and how bad the damage is.